So our next speaker is from Synopsys, Srobona Mitra, a senior R&D engineer. Srobona is currently senior R&D engineer in low-power static verification tool development at Synopsys in Bangalore, and prior to this she worked for India Systems and Technology Laboratory and IBM in India. She received an MTech and PhD degrees from the Indian Institute of Technology in 2006 and 2013 respectively. She has authored several international papers at several international conferences and journal papers in the field of formal, semi-formal, static hardware verification. And the title of the talk is Static Power Intent Verification of Power State Switching Expressions. Thank you, Srobona. 20 minutes as well, please, Srobona.
Yeah, thank you, Mike. Hi, I'm Srobona, and I'm going to talk on static power intent verification of power state switching expressions. This is a work that we have done in Synopsys as an enhancement feature on our low power static verification tool, and my colleagues who have worked along with me on this are Bhaskar, Somen, Rajoshi, and Kaushik. So going to the next slide. So first I'll discuss the background and what were the objectives for this work. So as Gabriel from Mentor Graphics discussed just now, low power architectural intent which is written in UPF and CPF, it undergoes successive refinements during the design cycle, and we have had several customers who are in the beginning of the flow, of the design flow, they are writing the power intent at a abstract high level. We call that logical power intent. This mainly consists of power domain supply sets and the power states of the supply sets in terms of their on-off expressions. So this corresponds to the configuration UPF that Gabriel mentioned, I think. So and the ultimately, when the design is going to be synthesized, then after going through several cycles of refinement, the power intent is finally consisting of all the low-level details like the supply nets, the supply ports, the supply port-to-net connections, the power switches, and also the power switch on-off expressions, which are all specified, and this clarity is often not there at the logical power intent level. So the requirement for this work is that the initial power intent remains intact through refinements from logical to physical. That has to be ensured at all points of time, and erroneous refinement steps at any step of the process can lead to functional bugs which would get manifested very late in the design flow. And so our goal here is a static checking methodology for verifying early that the power state switching expressions are equivalent through refinement steps. Now let us look at the current low power design verification flow. So in this picture, the logical power intent and the corresponding RTL design are the first things to be written, and we can see that through power intent refinement, finally we are arriving at the final physical power intent. And this goes through design synthesis, the PG netlist design comes, and that undergoes PG simulation. It is only at this stage when the PG level simulation is done that actual bug is caught, and this is already very late in the design flow, and so this red box specifies a bug fix which comes very late in the cycle when it is already prohibitively costly to implement any changes, any fixes in either the design or the physical power intent. Now let us look at what are the power switching expressions that we are talking about. So the add power state logic expression it is found in the logical UPF. It uses logic expressions to specify conditions under which the power net or ground net of a particular supply set will be in a particular power state. So basically it boils down to specifying on-off conditions for these supply nets, and that in turn, because supply nets are supplying the power domain, so that in turn turns on off the power domain whose primary supply is this supply set. Again, create per switch logic expressions, these are mostly found in the ultimate low level UPF that is being formed, and these can specify the on-off state conditions for a particular power switch policy through logical expressions on logic nets. That again translates to power domain on-off condition. So what we are trying to do here is take the add power state logic expression and the create power switch logic expressions, the corresponding ones for each state, and ensure that they are consistent. So here is the concrete problem definition. Given the add power state logic expressions and the create power switch on-off logic expressions, our goal is first of all to prove by static checking of power intent that these are equivalent, and if the equivalence cannot be proved, then we catch and report the corresponding violation early in the design cycle. And the real advantage is that we are doing it as soon as the physical power intent is available. We do not have to wait for the design to be available. We do not have to factor in the complexity that comes in when the design is included in the verification. So this is the main value add from this methodology. So here we see in this slide 6 I show the design flow with the proposed early power intent static checking. Here this part, the logical power intent, is refined into the physical power intent, and as soon as that happens, we are having this static checker here which catches the bugs at that stage only, and the bugs can be fixed early in the design flow in the power intent. So we don't even have to make any changes in the design, which is adding a lot to the time saving and the bandwidth saving. Now I actually go through a small example just to illustrate what I'm talking about here. So on the right here is an example chip which has one audio part, audio component, and a video component in it. And there are two power switches, the audio SW and video SW, and this audio on is the this logic net here, while video on is the logic net for this one. Now if we look in the logical UPF, we can see that add power state for the audio SS, the audio SS is the supply set for the audio domain. Create supply set audio SS, this is for the power domain audio inst, and for this the logical expression in the add power state is video inst video on or audio inst audio on, which means that basically the this power state should be on either when video on or audio on is on. While in the physical UPF we can see that ultimately when the power switch is audio SW is specified, then the on state for that is specified as enable. This enable, and the enable is the control port which is connected to only audio inst audio on in red here. So what happens ultimately is, in the scenario where video inst video on is on and audio inst audio on is off, we find that our audio SW power switch remains off, and that turns the audio PD off, which is actually a functional problem, because when the video is on, audio will not come because the audio PD has turned off, and that is just due to the erroneous refinement from this add power state command that was written in the logical UPF to the ultimate create power switch that was specified in the physical UPF. One point to be noted here is that I have separated out the logical and the physical UPF for clarity of illustration, but actually these will usually be part of the same UPF. It's just that the same UPF will keep getting refined, and slowly at the end of the towards the end of the verification cycle, these the constructs being shown in the physical UPF will come into it. Okay, so now we actually implemented this proposed static checking in the existing static checker flow, and this was run on some industrial benchmark designs. Moderately large as well as very large ones. The sizes are specified here, and in all the cases it demonstrates negligible overhead in terms of time and memory to the existing static checking runtime. So we are gaining a lot in time and bandwidth by catching the violations early or by gaining early confidence, and at the same time we are not adding any considerable overhead to the static checking timing, to the static checking time, and we are also able to report the inconsistencies, and that too at the physical UPF level itself and not at the design level. So I just go through the conclusions. So any inconsistency between the on-off state conditions between logical and physical power intent, it seems to be a very small difference in a logical expression, can actually result in a functional problem, but it showed in the example discussed. So this results in functional violations and manifest as a low power design bug, and that too very late in the design flow. So and another problem is, for simulation to detect it, simulation must exercise this particular triggering condition. Like in our example, the particular corner case scenario which had to be exercised is video inst video on being on and audio inst audio on being off. So that is another problem which this methodology will bypass because the main one contribution is completeness. It is guaranteed to find any inconsistency if it exists, since we are doing it as a at the full static level, and it's 100% guarantee if proved that the two expressions are equivalent. And the early catching of bugs is the other main value add, because we are able to catch it at the physical UPF level. So these are the references that we have used, and so yeah, thank you.
Okay, thank you, Srobona. Are there any questions from Bristol? Okay, so we've got one online question, which I'll ask. Srobona, we have one online question regarding more of a sort of property checking approach with this tool rather than an equivalence checking approach. Have you looked into the possibility of defining properties on low power that we're able to prove, maybe at the logical rather than the physical level?
So here, yeah, we are mainly talking about checking the equivalence statically. It's not really formal property verification, but we have looked into the possibility of generating certain assertions from the different specifications that are already specified in the UPF, and be able to verify that formally on the UPF and the design combined. The only disadvantage that we have faced as of now, the only problem that we have faced as of now in this approach is the power management unit also has to be a part of the DUT in some form for us to be able to formally verify any of the low power properties in a meaningful way. So, and that we do not often do not have in hardware as of now. It can also be in software. So that is the problem we are looking into. This is something that we are looking into, yes, but not yet in any productized form.
Okay, thanks, Srobona. Thank you.
Thank you.